We're going to go over Barron for your response question regarding confidence intervals on number 1. So you guys had this for homework, where a simple random sample of 1,000 voters found that 57% believe that competence is more important than character in voting for President of the United States. Note that this is a sample. This isn't based on a census. So we had to determine a 95% confidence interval, and then we had to answer a few questions. Before I jump into a confidence interval, I want to make sure that my conditions are met. Always make sure your conditions are met. That's important. So first condition, is it random? Yes. How do I know? They tell me it's an SRS right up here. That works. 10% condition. Is 1,000 less than 1/10 of all, let's see, U.S. voters? I think it's safe to say that 1,000 is less than 10%, so we are good there. The large counts condition. Okay, so it's telling me 57% of 1,000 people. So if I do 0.57 times 1,000, I'm guaranteed that that's going to be greater than 10. I'm in good shape there. Now, that also means that 43% of 1,000 didn't think that competence was more important, so I have to make sure that's greater than 10. I can safely say that 43% of 1,000 is greater than 10. So my conditions are met, and I can proceed ahead. If your conditions aren't met, I'd say just note that they aren't met, but you can still proceed ahead with the problem. So you notice I wrote the formula for a confidence interval based on proportions, and that enables me to kind of move forward and fill in my blanks. So I need my statistic. They give me that. It's 57%. So you notice I plugged that in here. I got my statistic of 57 or 0.57. I've also got that here to figure out my standard error, 0.57. And I also have its complement of 0.43, sample size of 1,000. Now I'm doing a confidence interval of 95%. So I'm going to need a critical Z here. I need to know how many standard deviations I'm going to need to go out from the center, or my statistic, to capture 95% of the possible statistics. Now, a statistic we're working with, we're using this as a point estimate. We're saying, okay, if this is the parameter, we're going to build off of this. Now, we don't know if it's the parameter, but we're going to use it as a point estimate. So we're going to take that 0.57, and we want 95% of possible statistics based on this. Now, you'll notice that if we want 95%, that means we have to go out a certain number of standard deviations in each direction. What I also noted was that if we're looking at 95% in the middle, that means there's an additional 2.5% that we are not dealing with. Those tails are important. That will enable us to find the critical value. If I use inverse norm, I use the area of 0.025, plug in my mean of 0 because we're going with z-scores or standard deviations, my standard deviation of 1 because we're dealing with z-scores, I get 1.96. And what that tells me is that I want to go out 1.96 standard deviations in each direction to make sure I capture the 95% of possible statistics right here. So what that enables me to do is I'm going to create a net that I'm hoping captures the true parameter, because we don't know if we're getting that true parameter. Anytime you do a sample, there's some variability regarding your population. So what I then did was I plugged in my critical Z, and I figured out my standard error. I did some basic math here, used my calculator, got 0.01566, multiplied that by 1.96, and I got about 3%. So that means it's going to be plus or minus 3%, which gives me a confidence interval of about 0.54 to 0.6. So that enables me to make the leap here. I can say I'm 95% confident that the proportion of voters, the true proportion of voters, my parameter, who think that competence is more important than character, is 54 to 60%. So that I'm 95% confident that the true proportion lies within there. I can also say I'm 5% confident that the true parameter does not lie in that interval. But we don't like to say that, but we can think that. So now the next question they ask us is, if your pairs know nothing, how do you explain to them you can't simply say that 57% of voters believe that competence is more important? Well, I'll tell you what, you can't say that because 57% is just a statistic. We did that out of 1,000 voters. That doesn't represent everybody. Even if we did a really good random sample here, you gotta expect some variability. So that's why we have this wiggle room. We can make an inference about our parameter, but we can't say that this is our parameter. It could be. There is a possibility. With it, 57% is in that confidence interval. It's between these two values. It is possible that we did capture that true parameter, but it's also possible we didn't. We might have just gotten a sample that was really heavy of people who were in favor of competence instead of character. It's possible that maybe only 1% of US voters think that that's more important. And we just happened to get a sample that was a lot different than our parameter. That happens. That's why we create these confidence intervals. It gives us a nice net to try and catch the parameter. And we can say, well, it could be here or it could not. And then they say, also explain your parents what is meant by 95% confidence level. What that means is they're asking about the level here, not the interval. What a level means is that if we did a bunch of random samples of 1,000 US voters, we just did a bunch of random samples of 1,000 US voters, and we did confidence intervals just like this one, we can expect to get the true parameter in about 95% of our confidence intervals. So that means 5% of our confidence intervals probably aren't going to get there. Like in theory, I'll draw a nice picture here to give you an idea. We really don't know what that parameter is. So it'd be right here in the center. We don't know what it is. But if we did a bunch of confidence intervals, right? Now, what you want to remember is, if this is your parameter, right? Within this normal distribution are all the possible statistics you could get from your random samples. All these p-hats. I'm drawing a lot of them, but you get the idea. There's a ton of them in here. These are all the possible statistics you could get by doing random samples in that population. Some of those random samples, if you do them, you'll get that true parameter right here. Those could be that true parameter. Some of those, say you do a random sample, even a really good one, you might get a statistic that isn't even close to your parameter. So what the confidence interval does is it gives you a range of values. So you build it off of a statistic, and then it extends out like so. Maybe you get confidence intervals that look like this. These are your intervals. Now, in these cases, they're capturing that true parameter somewhere in that interval. It might be on the high end, like up here. Might be on the lower end, like right in there. But chances are, you're catching that interval, you're catching that parameter somewhere in your interval. Now, if you have a confidence level of 95%, that means if you did 100 of these, 95 out of 100 would capture that true parameter, and 5 out of 100 wouldn't. So I wanted to walk through this question, give you a chance to see how I did it, as well as interpret it. If you have any questions, you know you can always reach out to me at my school email address, or you can reach out to me at gamoshstats@gmail.com.